All right, a lot of the rest I'm going to cover here is just a return to the basics. So I'm not going to spend a lot of time, but as we've talked about with the density bonuses and incentives, and just talked about with longitudinal joints, the importance of that is, to me, the middle one is the important one: reduce moisture penetration. Decrease air voids, increase density is reduce or eliminate moisture penetration into that mat. Moisture, I don't care what kind of pavement it is, 2-track, gravel, concrete, asphalt, moisture is the killer of pavements in our part of the world. And your first point of being able to address that is density or compaction during the paving process. So, and then the last one's important too, just like moisture penetration. Well, cold air penetration into the mat. Greater the voids, the greater the depth, and I'm not talking like 4 inches into the mat, but another inch of cold, minus 25-degree cold morning temperature at 5 a.m., 6 a.m. getting into that pavement has a lot better chance of inducing that thermal crack, that cold temperature crack. So, and again, I mean, you've probably all seen this if you came through when I was doing paving inspection, but basically the 3 variables are the 3 areas of variables, and the middle one, environmental, is the big one in our part of the world. Time, temperature, location. So how do we measure it? Well, in the old days there was basically 3 ways, and nuke gauge. Most of you probably used nuke gauge at one time or another in your career. Again, nuke gauge, though, has been, my experience, has been one of the most misused piece of test equipment I've ever seen, because unless you calibrate it can give you a reading, backscatter reading. If you set it up on pounds per cubic foot, it can tell you that. Is it right? Hell if I know. If it's calibrated, at least you got a good shot that it's right. And so when I meant misused, what I meant is that if you get out there and start using, unless you're just looking at relative differences between readings, the absolute value may mean nothing unless you've calibrated that nuke gauge. Non-nuke or electromagnetic type gauge measurements, they work too, but again, calibrated. So for acceptance, we've always done cores, but the one that's introducing now is the DPS, and it's quickly getting density profiling system, or basically using ground penetrating radar. So there's an old Transtech non-contact, probably seen 100 of those as I have. How do you measure it? Well, one of the things of taking cores is, number one, they can be highly variable too, depending on your drill bit and whether you get it perpendicular to the road and so on and so forth. And you're going to bulk out those cores in the lab to get your values, but it's destructive. It takes time, and it puts people in a very compromised position early in the morning out on live traffic on the road trying to get them. So here's the pros and cons. And again, that kind of my takeaway on this is that the thing is, pavement, it's not rocket science. It's like anything else. You get what you measure. And if you aren't measuring it, you're not going to get it. And so the importance here is you have to use something that you have some confidence in to do quality control. Cores are really the acceptance. You can't go out there in the middle of a paving job unless you have a lot of dry ice and so forth and take cores and check it. That's going to be the next morning. And so you might be 6,000 tons down the road, yesterday's paving and half of today's paving before you get your core results. So that means during the process, you need to be doing some measurement, whether it's using a non-contact gauge, whether it's using a DPS, whether it's using a nuke gauge. If you don't, you're going to get what you get. So that's where the DPS comes in. And again, I mentioned John, he did this case study on Highway 32, which north of Castleton a long time ago. It was the first run, I think. North Dakota DOT's part of this pooled fund job. The second one there, TPF5, Pren 443. Continuous asphalt mixture compaction. And I just want to get some data, and I think Kurt's going to show some as well. But the push here is, hey, I want to get as close to real-time data on density most accurately and cover the whole road. So why use the DPS? Well, this is John's. He says coverage, right? I can get edge to edge. I can get start to finish. But to me, it's also quickness, is getting that data when I can still do something about it at the paver and with the rolling operation. So you can see here, he ran these numbers, and this particular job, which was on Highway 32, they had 38% coverage. If you look at the coring method using, and this was before the 1,000 foot, 1 per 1,000 foot sublot, it was 2 for 2,000 feet. You can see the numbers there. So the DPS was not only giving you 54,000 times the information, but in my opinion is it's giving you when you can do something about it, particularly as a contractor and a project manager. So this data comes out. This is a histogram, basically. These are all the density measurements, voids converted to percent density, percent of GMM. And so you can see here, obviously the high points are where your average or mean is. And then from that cumulative curve there, you can see, okay, well, where was I at? Well, in this case, my minimum was 84.7. My mean was 94.5%. And I remember talking with John quite a bit on this early on. He said, well, yeah, but the cores only came out 93.5%. The DPS is telling me it's 94.5. Well, why is that? Coverage. Cores, we do them randomly, but they're still random, right? There's still a limited amount of sampling. And so that's one thing. The other thing is, and I had a lot of discussions with John and others, is, we typically fog seal the mat as soon as we finish it, right? Before we move traffic control. And so that affects the numbers. Well, yes, it does, because one of the ideas of fog sealing it is it closes up those surface voids, which means what? Your air voids go down, density goes up, because that's less space for water, moisture, air to get into. So this is one, I think, Kurt, I don't know if you showed this, and if you did, I apologize, but Kurt Dunn has done a lot of work on this. And this one, I thought he had sent this to me, and I thought it was really interesting. And I remember talking about this with Kurt when he was putting it down, but you can kind of see the template here. And these broken slopes are always a problem. And then of course you got your inslope here on the shoulder. So this is a continuous pass, shoulder and main line, obviously, but you have a broken slope here at 6.5 feet from the outside. And if you look up here, Kurt did a core right on the shoulder, which this had a paver mounted thermal profiler on it in IC as well. So you see in that area that core was taken basically on the fringe line, which is the light blue, which is basically 5 passes or less. Whereas the mainline core out here in the purple, that was 9 passes. Well, the mainline core was almost 97%. The reference core taken at the shoulder, which typically we wouldn't do for acceptance, was 88.7. So that's significant. With our type of mixes, the 12.5 millimeter super pave mixes in North Dakota, which encompasses 99.8% of all pavement done in North Dakota, basically, they're fine, dense graded mixes, just because there ain't a lot of rock in our part of the world. So that trigger point of where you go from impermeable to permeable as far as air voids is probably around 91%, give or take. So 9% air voids. So what's 89% tell you is that shoulder, that inslope is going to be taking a lot of moisture over time. And pavements, in a lot of cases, fail from the outside edge. Your most critical point is on any structural element is the end, and the connection, if you want to call it. And here it's connection to subgrade. So that can be, here's another one. And again, this is Kurt, different job. And Kurt's done more for looking at and trying to put the data together. But here's another instance. The informational core was 89%, 13 foot left of center. And typically in our acceptance procedure, you wouldn't even use that. You'd move it a foot in, right? And the mainline core, same location, was 94. And it's all about passes and temperature. In this case, passes. If you don't put something on it, you got to squeeze air out, and that takes energy. So there's the DPS. That's John in action there. And Kurt, again, I might be stealing a little bit of your thunder, but I thought this was pretty important. I kind of narrowed it down. But with the PWL, percent within limits, basically in PWL, you're looking at what's, given the fact that I can collect enough data, what's my average, but what's the variability in my density with all those cores I've taken. And if my spec limit, in this case, lower spec limit's 92.0, upper spec limit's 97.0 as your upper limit, I'm looking at that pavement I just placed in the compaction and saying how much of that is, in most cases, is over 92, right? And in this case, you use that data and you come up with some calculations. Kurt has a pretty good presentation on that if you want to walk through the whole thing, but you get a quality factor for that particular density operation. And this, continuing on that same job, you can see it was on North Dakota 17 and North Dakota 17. This is the actual data. If you plotted that all out and looked at it, the red lines are the upper and lower spec limits on density. Well, my average obviously is damn near on the midpoint of that, which is a great thing. And you want this peak to be high because the higher the peak is, the narrower the base is. So you can see here, you have this little piece here that was outside of the spec limits. And this is a statistical, pretty accurate statistical determination. This is also outside of the spec limit, but that's one of the reasons for moving it from 96 to 97. Was you don't want somebody to pull rollers off because they're getting penalized because they're rolling it too good. The whole purpose of the upper spec limit initially was you didn't want to overroll the mat. Well, my experience is if you overroll that mat, you start crushing aggregate and your density drops like a stone, pardon the pun. And so, you can see that in the field. You can feel that in the field. That'll take care of itself. I'm not so much worried about the upper spec limit. You just don't want the law of unintended consequences of somebody sliding this whole thing back because they're worried about this. So Kurt's data was the average density was 94.8, and this is 221 cores, mainline paving cores. The minimum one was 90.8. The maximum was 97.5, which accounts for this little right tail. If I can get my cursor working here. Right tail here. 6 cores were under out of the 221. 5 cores were over. So 97.3% of those cores representing that project's paving and rolling process were within the spec limits, and that's good. This is a study based on those original PWL jobs that I noted in that earlier screen. And I think Amy wrote this when she was in research. Of course, now she's state materials engineer. But this evaluated the results of those particular pilot projects. You can see the total density incentives on both of them up here. The size of the projects. One was in Valley City District on Highway 46. The other one was in Grand Forks on, I think that was south of Lakota on Highway 1. And so the kind of the important piece of this, and you can see the conclusions and recommendations, and this actually led to there being more PWL jobs. Down at the bottom right corner, you see that table, similar to that table we did. The yellow line is the historical data from all the previous FAA 43 jobs. And you can see it's kind of a squat, and it's very far to the left, almost on that 92.0, right? I think it was 92.7 or 6 when I showed you on the table. The green one is the Highway 46 job. The red one is the Lakota South job. And really, when you look at that, both of those PWL jobs showed their mettle, right? If you pay somebody to get that performance, in the case of, I think, the Highway 46 job, the contractor had a person just doing quality control, doing the measurements. I don't know if it was nuke gauge or non-nuke, but doing it. And what you're looking for is you want that peak to be near the center, that 92 to 97, and the peak to be high and the base narrow. And so quick layout. So intelligent compaction really came about, and North Dakota's really taken the lead in that. And this is some of Kurt's data too. And I'll run through these pretty quick because Kurt's going to follow. But the Highway 32, this was a job south and north of Findlay, and then it connected to up toward Anita. So it was a fairly long job. Had the pavement mounted thermal profiler, had intelligent compaction, so you could measure that CMV is what the roller is telling you as far as the resistance to the pass. The pass counts is the third line down, and then John was out there and ran the DPS, the DOT's density profiling system. So those are the three kind of lines you see here. So if you take kind of some points here was the random core location on this particular piece of main line was 93.3. You kind of see it on all four traces here, depending on what you're measuring. The DPS at the bottom there showed it was between 93 and 94%. But what's probably more important here is, particularly looking at the pass count, the third line down, is some of the variability in the number of passes on any particular spot on that pavement. And in addition, with the paver mounted thermal profiler, you pick up these paver stops. Here's two here. You can see the blue is obviously cold mix, right? In general, the temperature was between 240 and 250. This coming out of the screed, obviously. And this is surface temperature, not internal temperature. But every time you had a paver stop, you see a lot of blue. Meaning, you can't fool physics, right? Mother Nature is that mix is going to get cold. Behind the paver where you stop, that knockdown roller can try and get up as close as possible, but then they got to pull off the mat and wait for the next truck or the paver to start. But it also screws up your passes, because then when you restart, now the paving, the rolling operation has to get back into stasis, into what they're supposed to be doing, and that takes time. And you kind of see that with the DPS, is obviously between the temperature and the passes, is you see a drop in density at each paver stop, particularly following that paver stop, continuing on down the road. So I won't spend much more time on that, but you can see in this one on the far left, and again, these are Kurt's, comparing the same location, pass count, temperature mix. And this is from the intelligent compaction. This is from the temperature the knockdown roller's measuring in the lower left. And then you can see in this case, the three paver stops and what's happening. And then the DPS is in the lower right. Well, you see that kind of variability there, right? Is, as you got down the road here, you can see now I'm back into stasis after that paver stop, and I'm getting my 11 to 13 passes. Well, my density right below it shows that I'm getting back into the green and dark green where I want to be. But again, looking at that inside edge, we're talking about longitudinal joint on that first pass, free edge, you're only getting 85 to 87 to 88 to 90%, which, that ain't going to get better when you do your matching pass. So I thought this was an interesting one too. Same project on Highway 32. Actually, Melissa Corby with Interstate Engineering was on that project doing the project management, and Scotty was up in the lab doing it for the DOT. But the orange line here is the actual continuous IRI measurement. So you can see these, obviously where that line goes high is a rough spot or a bump. And then you can kind of draw your line on the baseline or the average of these and kind of figure out what your IRI is. And obviously the software does that on the IRI number. The green hashes here are paver stops. And the number in those hashes is the time that paver stop. First one at 882 plus balls was 10 minutes, and this one just before 890 was 48 minutes. And you can see each one of those creates a rough spot, which is going to impact the ride and might be a bump grind, right, that you have to do. So, direct cause and result there. And this kind of finishing up, same job, Melissa had put this together. Two parts of this job I mentioned. It was a combined job, the Findlay section, which most of the pictures were from, and then up toward Anita. The plant was up by Fordville, so it was like a 60-mile wet haul. But I thought this was interesting because with the paver mounted thermal profile, you knew how often the paver was moving and how often it was stopped. And you can actually calculate paver running speed too. But the percentages is what kind of drew my attention. Was Finley section, that's mostly a tangent from north of Finley all the way down to actually the 200 cutoff. Roughly, the paver was only moving less than 2/3 of the time. If you added it up out of the 9 days paving, basically almost a day and a half of that paver wasn't doing anything, which tells you a big story about productivity, right? In a short construction season. But after looking at that previous data, you know that 1.25 days is not only a productivity penalty, but you end up with a ride penalty and a density penalty too. So, you know, a lot of times from an inspection standpoint, it's not how fast you're going, it's not stopping. And it's going at a continuously speed. It's like the tortoise and hare, right? Is don't sprint out and stop. It's tortoise approach. You know, a lot of times the correction for, in my experience, 70% of paving problems is drop your paver speed down 8 or 10 feet per minute. And a lot of those problems go away. Now you have trucking issues and so forth, and trucks break down and pavers break down and so on and so forth. But if your goal is to get good ride and good density, the only place you can start from is, and the best place to start from is keep that paving continuous and, you know, eliminate as many stops as you can. If you have to stop, which you do sometimes, is short stops are much better because they create less of a bump, number one, but they keep the thermals, the temperatures more consistent. So kind of running through, this was, I call this the specification incentive tug of war. We just discussed this at the break, but this is actually limited. It's only 5 sets. Aaron Perez did these, and I think they're working on more of these. It's kind of the tale of 5 projects, right? Depending on whether they had incentives and disincentives. Do I go for density here? And this was prior to the 1.05 or whatever. Or ride here and the bonus. So these are actually PCN numbers, project control numbers. These 3 jobs, yeah, they got great ride and got bonuses, but their density was, you know, 1% lower than these 2 jobs. They got, in one case, a nominal penalty and nominal incentive. So how you place those numbers and what you put them at obviously has consequences. And the consequence we want is to spur better quality, make quality a competitive advantage to the contractor. And when you have that, you know, you'd expect to see these 5 points almost, you know, each project's different, you know, from a ride standpoint and so forth, and each project's different from a density standpoint. Is it a mill and fill? Do I have weak points in the substrate? I mean, all those things come into play, but ideally, you want all 5 of these points to be together, maximizing the incentive on both ride and density. So some quick updates, or not updates, but just remember the admixtures, and you'll see more of this. Evotherm's approved to date as far as a paving admixture, and it's been used a lot in North Dakota. I wanted to cover SMA really quick. It's basically just a coarse, gap-graded, rut-resistant surface coarse mix, strong aggregate skeleton. And you build a binder mastic. That's where the M comes from. Binder mastic it's gap graded. So you have a lot of rock, 3/8 say rock, but you also have a lot of fines and nothing in between. And the fines are what you're using. In fact, a lot of times you put a dust in, like fly ash or crusher fines, because you need to build that up with a higher asphalt content to create that mastic. And then typically you add some type of cellulose or drain down pattern. So you can see it when you look in Mark's on here, I know, and he did the most recent SMA job in the Fargo district, is the difference between the gap grade. The left one's the SMA, right one's the dense graded. I mean, same size of rock, it's just the gradation. And you can see the amount of mastic is much more apparent than the one on the left. There's some guidelines out there. And I know I talked to Mark quite a bit before that project, Kim, Kurt, and I just catching up, but a lot of data going back a long ways. Basically, with an SMA, you can eliminate any type of rutting. And this was an NCAT study probably 20 years ago that a quarter of the projects after their design life had no measurable rutting. Because they're high in asphalt, that typically have less cracking too. So here's some other studies. Interesting part is the bottom one is because it looks open textured when you place it, but it's still impermeable. But that'll absorb sound as well. So research has shown it can drop traffic noise, tire noise by 2 to 7 decibels. You can do it in different nominal maximum aggregate sizes. The summary, and this is probably, if you have an SMA job, Mark would probably confirm this, is it's a premium. It costs more money. It's got your highest or most aggressive asphalt binder, PG binder. It's got a lot more than a dense graded mix from a total asphalt content, and it needs high quality aggregates and some additives. But basically, you get a high friction, low wear surface, eliminate chip seals or any type of surface treatments. The yield or the spread rate, when you look at it that way, is relatively low, 1,300 tons per mile on a 26-foot wide section. But you have to watch out for these things in the field. It's tougher to compact. If it's tougher to rut, it's going to be tougher to compact. So you have to kind of think differently when you're looking at your screed and your paver and your rolling operation. This load out and handling, you have little room for error. This high mastic makes it really sticky. Basically, handwork is damn near impossible. You start looting this stuff out. It's like trying to spread peanut butter on a smooth surface. You need really consistent production. That applies to any project, but particularly with SMA. And believe it or not, it's prone to segregation. Thermal segregation. It's relatively thin lift because it's a pretty aggressive PG binder. It's typically produced at the plant at a higher than normal temperature because of that PG binder. And generally, what you're looking for in the design is you need this lockup. You need the stone on stone contact. And you can feel it in a gyro if you have it right. So your spec limits change to 94 to 97.5. But the segregation can occur in placement is with that much rock. If you end up segregating it, in most cases, when I've seen it segregated, it's by the placement, by the windrow and hull and placement, is you kind of eliminate its benefits. Let's put it that way. So the first one actually was in South Dakota, in our part of the world, down, 20 years ago now, south of Sioux Falls. Here's kind of a list of North Dakota's project, including that bottom one in the Fargo district last year. This was I think this was the first one. This is from Hankinson South. In fact, that's in the background. There's the casino state line. You can see it's a super paved mix. It's just different gradation, different objective. But this, from an inspection standpoint, this is what you're trying to look. This is a fat spot where you get some of that oil kind of migrates in the mix to the surface. And that's why you're feeding fiber into that operation, is you want to keep that asphalt. You don't want it in the truck after it dumps its load. It costs a lot of money for that asphalt. And you want it in the mix and homogeneous in the mix. And generally, you start seeing fat spots, you need to check your fiber load, make sure that you're controlling that drain down or run a drain down test so that you don't end up with these kind of puddles of asphalt. So the lower left is cellulose fiber, basically that's chewed up and baled newsprint. So, and the right side, lower right, is the fiber feed, which is generally done on the baghouse fines return. Clear line so you can make sure the fiber's feeding and chewed up. So again, quick run through here. You're trying to squeeze air out. As you do that, you decrease the permeability. When you decrease the permeability, you end up getting double for the dollar because you're increasing the fatigue resistance of that pavement. So kind of the end result, and you've seen this before, but when we look at compaction, we generally spend a lot of time with the plant calibration, mix design, the whole works. And sometimes we tend to forget that, that doesn't cost much, but the compaction process from screed on back through your rollers is just as important as any part of this process. When you look at compaction, it's about temperature, unless you're using some type of admixture. The three things, those are the three A's I talked about earlier. The environmental variables and how they affect you in the roll down and paving operation. It depends on layer thickness, your ambient temperatures, your substrate temperatures, your mix laydown temperature, and wind, and the angle of the sun. Angle of the sun gets pretty low, late season paving and early season paving. One big improvement, the first piece of compaction that we do is actually in the paver. It's on the screed. And you've seen over time now, particularly with increases in ride incentives, heavier and heavier screeds going on pavers, which generally leads to heavier and heavier horsepower on the paver. And now, can't remember, it used to be called a DMX screed. We're seeing those kind of introduce the market, a little different than a smooth steel screed. Some changes, but it's all about what type of force, how much force do I use to squeeze air out of the mat. And things to remember, PLI, that's pounds per lineal inch. It's basically weight on that axle divided by the width of the drum itself. Pneumatics are different type of energy, as you saw in that previous slide. Very effective because they knead the material into place. When you're making bread dough, you don't just pound on the top with a square face hammer. You get your fingers in there and knead it. And so you're doing basically the same thing. Pickup's usually the issue there. And again, with some of the products, non-hydrocarbon products. But the key there is if you see a pneumatic pulled off and it's doing its job and you're getting target density, but it's because of pickup, then it might be an operational issue. Pneumatic rollers like a shark. It always needs to keep swimming. And so it needs to keep moving on hot pavement to keep those wheels hot. Vibes, pretty standard. Amplitude, frequency, impact spacing is the thing to watch. As you see on the right-hand side there, we want an impact spacing between 10 to 14 per foot based on the frequency and ground speed of that roller. So amplitude's just the distance up or down on that roller. And again, that's adjustable. The mix will take it. High amplitude's good, most energy, but some mixes can't take it. Some thicknesses can't take it. Impact spacing, again, you can see it with your eyes if you ain't hitting it right, because you get the right shadow on it. You see those kind of ripple marks, but basically roller speed in feet per second divided by the frequency you're set at with that vibe roller. So again, explanation there. So again, to get there, you got to measure it. Some do's and don'ts. Obviously, most of you already know this. You never roll off the edge. You're not going to roll off that edge there. You'll never make that smooth. Ripple marks, again, just a matter of roller speed, ground speed. The thing here I wanted to mention, and you can see this upper right-hand picture is a picture from one of the national documents. The lower right one is one I took, is you can kind of see, and I bet you this was probably a paver stop, is you get here, now it's rain, but it's not raining now, so things are starting to dry out. And you see these dark spots? Sure sign of low density or high air voids, because that moisture should be a sheen, right? Just like a specimen or core or a gyro sample in SSD condition. And that moisture is disappearing into the pavement. And segregation will cause that as well. And here you can see it. That's one thing you're looking for out in the field is I don't want to see strips like that. If I do, I'm getting segregation. Could be a paver feed, could be a mix issue. Now you need to work from the back and work your way to all the way back to the plant sometimes, determine how that's happening. And the paver mounted thermal profilers give you the first kind of line of attack, as you can tell those spots. Look at the lighter color here. It almost looks like an end of load and a paver feed problem, right? Because I can do the same amount of passes, but they're much less effective on 160-degree mix than they are on 223 degrees. So my density is going to be lower. So again, remember the cessation temperature, that's the temperature at which no energy is really not going to squeeze the mat, but has more likelihood of damaging it. It's generally about 175 to 185 degrees Fahrenheit, depending on the mix. Now, if you have evotherm or some type of additive in, that number can drop, but that's your warning. So if you haven't done it already, and I stress this in pavement inspection year after year after year, but there's a tool out there that can tell you. You can enter your environmental variables, and it'll print out time to compact to get to my 175 degrees, basically. And in this particular case, same mix, same paving operation, same rollers. The difference here is what delivery temp did I have? The red line is if it was delivered to my paver at 300 degrees and rolled at 300 degrees, I had almost 35 minutes to compact it. Same mix, same paver, same rollers. If now it's only getting to my paver and into the hopper at 250 degrees or behind the screed at 250, now I've got less than half that time to get the same density. So that's your takeaway here. So this is what you get. This is the original pave. It's called Pave Cool. As you can see in the upper hand there, you can enter your binder type, the wind, air temperature, the type of mix you're doing, the surface you're paving on, your latitude, so you know what that sun angle is and the date. And it'll print this out, and it's really accurate. It's been around for a long time. You can download it from the MnDOT site, or you can just Google Pave Cool Minnesota DOT, and you can download this. And there's an app, you can download it on your phone, on your tablet. So I think version 3.1 now. I probably still got 3.0 on my laptop here, and that's your entry screen basically to enter your variables. And when you do that, you can run scenarios, late season, early in the morning versus late, middle of the afternoon, and very, very accurate. It's a good tool to have in the inspection field when you're looking particularly at early season paving or late season paving. That and a thermal mounted profiler, a paver mounted thermal profiler, and IR temperature gun are indispensable. And that's why, because if you don't get an effective roller pass, right temperature, right number of passes, basically, as Amy's report showed, a 1% increase in air voids takes off 10% of my pavement life. 20 years becomes 18 years. So, and that's been proven in a lot of data. State of Washington, the study they did, multi-year study, I think 7 or 8 years across the entire state, the Washington State DOT, having a problem with segregation. Of course, they have a lot of rock, and at least near the mountain ranges in those states too. But by controlling segregation in this rolling pattern, their overall pavement management showed a 50% increase in service life. I don't know what they were doing before, but that's a pretty good one. Again, we talked about this special provision, the standard special provision for longitudinal joint density, as somebody brought up at the break, and I guess it goes from 40 cents down to a 360 penalty, but that's per lineal feet, and that's a standalone deal. Now, the notched wedge joint on projects is allowed. Again, SSP4 is standard special provision, and if you can do it, I mean that the notched wedge facility has to be on the screed. But it's a much safer and, to me, better performing joint than just a vertical butt joint, because your tack is staying in place. So when you spray it and the water breaks out, but you're also compacting against something. But don't underestimate the tack coat. This one I've had for a long time is a picture I took quite a few years ago in southeastern South Dakota. Well, what you see there is not tack. I don't know, I guess it's delineation to keep you on the road if you've had too many to drink. But I'm sure what happened here is county road is that they had so much tack, and the county road supervisor said, hey, take that load out and shoot between so-and-so's place and so-and-so place. We're going to go out there and do some patching. Well, didn't have enough to spray it the whole way, didn't know where they were going to patch, so spread it out too thin over 4 miles instead of the right shot rate where they were going to patch. Because this is what you're looking for. This was a North Dakota DOT job. This was down by Mott. I mean, that's what you want to see. And it's a relatively cheap item in the big picture of the project cost, far less than your stormwater prevention probably. So, it's very rarely have I seen one overshot. And if you do, you can tell it on your boot when you walk on it. So, but not shooting enough, you just wasted time and money. Last thing I was going to close on is the edges. Why do we worry about the edges? That's non-pay tonnage, right? Outside that fog line. Well, there's why. I mean, more and more in our part of the world, heavy loads, oversized loads, where do they run? On the pavement edge, on the shoulder, where we don't even necessarily worry about compaction and ordinary compaction, right? So you need to roll that edge, particularly the inslope, the slough, because to get it closed off, you saw some of that data from earlier. And Kurt had sent me this just a couple of weeks ago. Where's that water coming from? Well, it's not a pavement defect, but it's a good shot. Is that those rumble strips are like cisterns. They store water there. And in this case, obviously the main line's dry. Is what's happening to all that water? If you got a lot of air voids in that area, where's it going? It's not going out and daylighting out to the edge of the pavement and into your borrow ditch. It's going into your pavement, which is going to weaken that weak area already. So there's retrofitted rumble strips on an old longitudinal joint. So this is the lift thickness. And again, this was from a South Dakota job. Lift thickness was too thin for a 12.5 millimeter. What happened? Trying to get density, you're just breaking aggregate. You violate that law, Mother Nature's going to come back and tell you about it. You see the cracked aggregate. Density on these cores was like 87%. So that kills you on PWL. In this case, it wasn't their fault, but the sure sign from an inspection standpoint, you start seeing white spots on top like this, it's thin lift with too big an aggregate, because those white spots are broken aggregate. So really the best range is you want your lift thickness, and this is the narrowest, the most minimum lift thickness on your job, to be 3 to 5 times the nominal maximum aggregate size. So that's in most cases 1/2 inch or 12.5 millimeter on North Dakota Super Pave. These thin lift mixes you saw in that test section south of Bismarck on 1804. Again, doing thin lifts, meaning 1 inch or less, as I think it was 3/4 inch for one of those test sections, is you're using a smaller nominal maximum aggregate size mix. In the case of those test sections, it was a 4.75 millimeter and a 9.5 millimeter. And so these can be good tools for pavement preservation, for designing into the pavement, for urban applications. I bring that up. I'm sitting here in Pierre, but been in Pierre for 20 years now. Worked a lot early on with their staff for almost 10 years now. They've been using 9.5 millimeter, actually a 6.3 millimeter super pave mix for all their street overlays. And in some cases, they don't even have to come out with a grinder and do curb reveals, so that you can taper them in. So number of different jobs in the city of Sioux Falls. Kurt was down on a couple of these as well. You can see the old pavement here, pretty poor condition. This was about $28 million to rebuild and reconstruct this section. So obviously that wasn't going to happen, not counting the shutdown of the roadway while they were doing it. So did some repairs, did some scratch profiling, and then did some thin lift overlay. And this was about 6 months after that job. And this is basically a 3/4 inch lift of super pave mix using 4.5 millimeter nominal maximum super pave mix. This one did have a juiced up PG binder because it's thin lift and wearing course. But a lot of different ways to go about it. I'm glad that the lab and the DOT put those test sections down on 1804. But good way to get some additional material down. So again, I'm running through this, so I give Kurt some time, but ideal candidates where you just have surface distresses, micro milling, where you can catch it ahead of time and put a thin lift down. Small amount of money, small amount of mix can go a long ways. These two are not examples where you'd want to use the thin lift. So